All right. Yeah, well, good afternoon. This is Bert de Vries. We are doing here this is the third lecture, but it is class number 4. And this is really about Bayesian machine learning, right? This is, I would say, together with the previous class on probability theory. This Bayesian machine learning is a straight application of probability theory. This is the theory of this class. After today's class, we will talk more about realization of Bayesian machine learning for different models and how to do inference in those models and so forth. And we'll look at applications like classification and regression and other applications. So the hardest part really is behind us if you understand this class well. And I want to make a few comments on this class. I'm going to share my screen. And then after that, of course, I will be open to take your questions again. So let me just share my screen. See. Okay. I hope you see. I'm just playing a bit now with MS Teams so I can still see if you raise your hand. Okay, so hopefully you see my screen now. These are the lecture notes. And I want to go a little bit through this Bayesian machine learning recipe again. There's something new or something special about this, and that is that almost no matter what your problem is, you always use the same solution method. You specify a model. It's up to you to propose any model that you want, but it has to be a proper probabilistic model specification. And from there on, everything is, in a sense, automated. You want to maybe incorporate some data, right? You've made observations and you want to say, oh, I want to teach my model to be consistent with the data set. Well, you can do parameter estimation. And you want to evaluate how good is this model? Maybe I should have taken another model. Well, you can do that with probability theory, right? Just like parameter estimation, just probability theory. You don't have to come up with some smart algorithm to estimate your parameters. You just follow the rules of probability theory. And the same thing for evaluating or scoring your model. And again, the same thing for how to apply your model, whether it's for prediction or for classification, is just following the rules of probability theory. If you do that, then you follow what's called the Bayesian approach, right? This is what Bayesian approach or Bayesian reasoning, Bayesian machine learning is all about. Is basically a commitment to using probability theory to do all your tasks. So you always begin, whatever your problem is, you begin with proposing some model for how the data is generated, right? So this is a model, let's just label it M. This model has parameters. Theta could be 100 parameters or 2 or 500, right? And you say, well, X, I can run that model and the model can generate observations X. We call this the data generating distribution. And then we also say, and this is really necessary, so what do you really know about proper parameter values? And you specify that in a prior distribution, probability distribution over your parameters, right? Once you have specified these two probability distributions, then everything from now on is in a sense automated. So, for instance, if you want to do what's often called machine learning, namely learning your parameters, updating the parameters of your model, well, you just can use Bayes' rule. Right? The Bayes' rule is nothing than a reincarnation of the product rule of probability theory. What's interesting about this rule, this Bayes' rule, so you specify here the prior, and you specify this likelihood, and basically everything that the data has to tell you about the model, or that the data can tell you about the model, is incorporated in this likelihood. There's no other place in machine learning where, let's say, the data has a way to affect your model. It's only through the likelihood. The likelihood specifies the relationship between, well, how can data affect my model? This, the denominator, what we call evidence, is really just P of D given M, right? I mean, all of these probability distributions are really given M. We call that the evidence for a model. And it can be computed by integrating the numerator over theta. So this is not something you specify. This is really the result that you want to compute after specifying a prior and after specifying a likelihood. Then you can compute the evidence, and once you have computed the evidence, well, you can execute, let's say, this division, and then you have your posterior. Now notice that the information that you put in here on the right hand side is everything that you know about your model, about your model parameters, your prior P of theta, and everything that the data tells you about the parameters in a likelihood. Now, how do you combine these two sources of information about your parameters? Well, Bayes' rule prescribes you have to multiply them. But this distribution on the right-hand side is exactly the same distribution as on the left-hand side here. That means that in machine learning, namely sort of executing this rule, there is no extra information gathered, right? I mean, all the information was there. It was in your prior and it was in your likelihood, and now we're going to combine it. But there is no extra information. There's also no loss of information, right? All the information that was in my prior and all the information that about theta that was in my likelihood is properly combined into a posterior. There's no loss of information and there's no gain of information. So in a sense, everything was already predetermined. Once you have specified your likelihood and once you've specified your prior, it's all predetermined. Right? So that's, I think, important to realize. Now, this term P of D is really P of D given M. We call it the evidence, and we say, yeah, the evidence is really what you're going to use to score your model, and that's an interesting idea. So I mean, hopefully you've gone through all this. We compute here model posterior, but somewhere here I say, okay, Bayesian evidence as a model performance criterion. Why would it be a good model performance criterion, right? That's an interesting question. And so it turns out that this expression, the log of the evidence, the probability of the data given the model, you can, it's kind of a weird evaluation, and maybe other people can do it in a better way, but you can rewrite it in this form. This here on the left-hand side, the log of evidence, is exactly the same as this. Now, what is this first term? Well, it's basically the likelihood, right? And we integrate out here the parameter. So, and what kind of distribution? Well, the posterior over the parameter. So after we do machine learning, after we incorporated the data. So this is sort of a predicted likelihood. It predicts how well will my model fit the data. So this is called data fit or accuracy. You want to maximize this. You want to be able to predict the data as well as possible. And so this you want to really maximize. Is that the only thing that you want to do? So maximize the data fit? No, because there is a penalty for learning, right? This term is technically a KL divergence. I'm not sure if you've heard of that. You can also interpret it as a mutual information. But you can, if you look at it as a KL, a Kullback-Leibler divergence, and we will get to that later in the class. Maybe I should have actually put it here. but you can think of this as a distance measure between the prior for the parameters and the posterior for the parameters. Right here, you see in the denominator, you see this is the what I knew about state of knowledge about the parameters before learning, and this is after learning. This whole thing is called the KL divergence. Just think of it as the distance between these two distributions. If they would be the same, this integral would be 0. And if they are different, this integral is greater than 0. And if they are more and more different, these two distributions, then the KL divergence will increase. You want to minimize this, right? Because actually, this is sort of like, okay, how much do I need to change my mind in order to fit the data? I proposed a model with a certain prior, and then I give a data set, and we can change the data. We can change my belief over my parameters by going to a posterior, and I can let's say make a new posterior that will make this as maximum as possible. But there are limits, because if I change this posterior such that this becomes totally maximum, and I don't even care about what I previously believed, I may have come up with a belief over parameters that are completely different from what I believed before. And you can ask yourself, is that still, yes, it's still the same model, right? I mean, you want to sort of not forget what you already know and still incorporate, let's say, what the new data set tells you, but not forget everything from the past. So by minimizing this complexity term, you kind of also remember what you already knew. And so there is a trade-off between, yes, I want to fit the data, my new information as well as possible, but I don't want to forget the past, what I already knew. And that's this complexity term. I want to minimize that. So this nice trade-off is a good interpretation of well, what Bayesian evidence is, and why it is a good measure for scoring how good a model is. Notice, however, that the evidence of a model is not a function of its parameters. So when I choose a model M, and I choose a data set, then this kind of this evidence is kind of fixed. I cannot change the evidence of my model by using Bayes rule for updating my parameter set. That doesn't change the evidence. So machine learning, if you think of it as updating the parameters or updating beliefs over parameters, it doesn't change how good the model is. You will need to have to change your model structure. You have to come up with a different model if you want to compare models, right? So those are a few comments that I wanted to make. So one thing is, in summary, that you can do everything that you need to do in Bayesian or in machine learning in general with probability theory. You can learn parameters, you can score your model, you can use it in predictions or for classification. Everything just follows from a probability theory. And the second thing that I think is interesting is to try to understand why model evidence is a good measure of performance, that it actually incorporates, it balances in a nice way without any tuning parameters. How much do we learn from the new data set, and how much do we remember from a prior? And the prior may be something that you have learned from a previous data set. So that's what I wanted to summarize, and I think it would be good if we go to questions. I know somebody already asked me questions at the beginning, so I think Sweda, but I will get to your questions. I see a question now by, okay, I'll just go from the list top down, and I see G. Bala. You want to post your question?
Yeah. Am I audible?
Yeah, you're audible.
Yes. So my question was related to the evidence that you were talking about just now.
Okay.
So, in the section where we talk about how evidence is used as the measure of, or how we can use it as a comparison of models, like as you said, we had split it into two terms, which is the data fit term and the complexity term. And we say that ideally we would want a model to fit the data well, and at the same time learn information from the model very easily, right? So it should have a high data fit term and the complexity term should be lower, right?
Yeah.
So in effect, the Bayesian evidence should be higher, right? But
Yeah. You want to
yeah,
choose models with high evidence. That's correct.
yes, yeah. So the one thing I was doubtful about, so in the lecture notes itself, we say that the Bayesian learning actually automatically helps us get a model which has like a high data fit and a low complexity. So I found it difficult to understand how the the Bayesian learning process automatically gives us this kind of an ideal scenario. Is my interpretation wrong, or is it yeah, can you just clarify that point?
Yeah. So once, I mean, our goal, of course, is to get, let's say, the best model with the best performance,
Mhm,
right?
mhm,
But what we call one model here is a prescription for a data generating distribution plus a prior. I mean, so basically, if you multiply these two, it's a probability distribution over X and theta given M.
mhm,
That's what we
mhm,
call, let's say, the prescription for model M. Now, if on top of that, I add a data set, I say, okay, and here's a data set. And so here's a model P of X comma theta given M. And here is a data set. Then technically my evidence for that model has been determined. It's just a matter of plugging in the data in your X and integrating out the
mm,
thetas,
yeah.
right? And then you have your model evidence. And if you can do perfect Bayesian inference, if you can compute those integrals, you'll get a number.
Mhm,
That is just a scalar because let's say you plug in values for X.
mhm. Um, Sorry, I think your audio is not coming out. Still not coming. I don't know if it's this mine.
About now?
Yes, yes. Now I can hear
Okay,
you.
okay. So sorry about that.
Mhm.
Then I will. I'll try it again. I don't know because I don't know where my audio left out. So once what we call a model is a prescription for a data generating distribution plus a prior. So
Mhm,
technically, if you multiply the data distribution with the prior, you get P probability distribution over X comma theta given M. And we say,
mhm,
okay, that prescribes, that's the specification of my model M. Now,
mhm,
if I add to that a given data set, so a given set of observations for X, then the evidence for that model is given. So that evidence is just P of D
oh, okay.
data given the model, right? That's what we call evidence, and that is a scalar. That's just a
Mhm,
number. It scores it. What does it score? Well, we can go down to the formula, and it's just an interpretation, right? But
mhm,
the interpretation is, well, it scores on the one hand, it sort of scores how well does the model fit the data, how well does it predict the data, And on the other hand, how much did I have to change my beliefs? I used to believe this prior, but in order to fit the data well, I'm going to have to, I'm going to go to a posterior distribution, and I change my beliefs a bit because, yeah, if I see new data, I am allowed to change my beliefs a bit, right? But not too much because, well, you shouldn't just throw away your prior. I mean, if you have good reasons for it, right?
Yeah.
So technically, that evidence for the model is completely given. You cannot make it larger or smaller other than by choosing a different model.
Model.
You can choose a different model. Now, then you can say, okay, how do we choose different models? And well, there are different ideas there, right? In nature, well, your model is your genotype. So natural selection is a process for generating new models, right? We are all, in a certain sense, models of the human, or trials of the models of the human race, right? And our genotype is a model, and then as we go through life, we collect a lot of data, right?
Yeah.
And but in engineering, they also try to mimic that, and they have genetic algorithms to generate new models, right? There are other ways, but it goes beyond, let's say, today's class. I think for today's class, the what you should remember is you choose a model, and what is a model? It's a prescription for the data generating distribution and the prior. And once you then observe a data set, you can say, what is the evidence for my model given this data set? P of D given M. And that is a good score for a model because it
Got
has this nice sort of balancing act between looking at the new data and looking at the past, namely your prior.
Got it.
Right? There is also a relatively nice interpretation of that complexity term in nature, because I mean we'll go through this later in the much later in the class, but I mean there's a lot of evidence that let's say the brain does something that's very close to Bayesian computations, and if you think of it that way, that okay, we observe sensory data and we learn from it, right? But this term sort of minimizes the change of beliefs. This is sort of how much computations you do. So that means that yes, we learn and we perceive and we do all that stuff, but we try to do it for a minimal computational cost. So the brain is energy efficient, right? That's also nice because this sort of also scores how much computations you need to do.
Got it.
Yeah, is that?
Yes,
Okay.
that is clear. Yeah, I just had just one more question, if that's okay. I'll like a from a similar section, but yeah, should I ask that question now, or how do I?
I think you can ask it now.
Yeah, okay, cool. Yeah, so this was regarding the point estimates section. So there we talked about how we can we talked about the maximum likelihood and the MAP estimate. So this is just one like practical oriented question. So my doubt was we talk about how like as we get more and more data, the contribution of the prior decreases and the likelihood, seems to overpower the map estimate. And I guess that is the intuition behind why we say that the map estimate converges to the ML estimate as the n increases. So my doubt is like in the practical scenarios, we'll always have like a huge amount of data, right? So then how would the map estimate prove to be useful in that kind of a scenario?
Um, if you indeed, well, I question your remark. We always have a lot of data. I mean,
Okay.
in the
Yeah.
deep learning community, they always think they have. I mean, they only you can only apply a deep neural network if you have a lot of data. So they choose problems with large data sets. But if you let's say if you try to ride your bike and you fall, well, you have to learn about how to ride the bike, but you kind of want to yeah, learn from as few trials as possible, right? You don't want to spend 10 years to learn how to ride a bike, so you want to do it as fast as possible. So so there you haven't usually, let's say, the real world, when you don't have a big database, or data can be very expensive, like in astronomy or in medicine, right? It can be very expensive to collect data. Then you don't have a big database. But the essence of this, from posterior to point estimate, is that indeed, if you have a lot of data, well, then obviously, in some sense, let's say the likelihood will become more important than the prior, because the prior is fixed, and well, you get more and more and more data, more, if you will, evidence about the about the behavior, right, from the data set. So that will overpower the prior, and in many practical problems, it really helps to use just a value for a parameter. And then this section says, well, how do you go from a posterior distribution, let's say P of D of theta given D, how do you go to, how do you pick your point estimate? Well, that's not a Bayesian question anymore.
Yeah.
But now it's a decision you need to make. It's technically this decision theory, and yeah, it just, whatever you choose, it's just an expression of what you care about, right? Do you care about the mean? Do you care about the mean and the map have different robustness properties, right? So it depends on what you care about. But this is no longer a Bayesian question. This is, you are starting to make an approximation now, right? The proper way to express what you know about parameter values is through a real distribution.
Okay.
Okay, then Sweta.
Yeah, so my question was regarding the beta distribution plots. I was not able to understand how the peaks change depending on the values of alpha and beta. Um, that was basically
These
my
plots
question.
here.
Yeah.
Okay,
Yes.
okay, so you should think of these plots here. This is a distribution for mu, right? And mu is the probability of heads, or is it the probability of tails? I don't remember. I think it's mu is the probability of heads. So, and we say, okay, so mu has to be a value between 0 and 1. And in if we do Bayesian machine learning, well, we have to first say, what do we know? What's our prior distribution over mu? So I have to choose a distribution. And it turns out that for this particular model, if I choose this Bernoulli distribution as my data generating distribution, then it turns out this beta distribution is a very convenient one. The beta distribution is, in this case, a distribution over mu, right? Not over the observed outcomes, the throws x, but over mu, the parameter of my model. And beta distribution has two parameters, alpha and beta, and what and those you can choose. And what you can express is, if you choose both to be one, then basically you say, I have no idea about this coin. If it's a fair coin or biased coin, I give every possibility the same prior, let's say, confidence, right? If you choose A is 0.1 and B is 0.1, you're saying I have a very high confidence that either I'm going to see a lot, that it's a very unfair coin, and I'm going to see a lot of heads or a lot of tails. That is your prior assumption for this coin, right? This coin could be, you look at this coin and you say it looks so crooked, and let's say that this is definitely not going to be a fair coin. So the probability mass around 0.5, which would be, if it would be a fair coin, I would have a lot of probability mass around 0.5. It's going to be low. Right? I mean, this is, I don't know what a coin like this would look like for you to choose these values. It's a strange coin, but at least there are parameter values that allow you to express this belief that it's going to be a coin that either is going to fall most of the time on heads or most of the time on tails. If you choose, let's say, more reasonable values, like let's say 2 and 3, here basically you're saying, well, I think that most of the probably it's an unfair coin, and most of the time it will land on tails, but I'm not so sure, right? I mean, let's say the probability mass for a fair coin here is the fair coin would have a spike, would have a delta on 0.5, right? You say, but here you say, I will allow every value for mu is still still an option, but my highest prior belief is that mu is around, let's say, 0.3. So that means that out of 10 throws, or let's say out of 1,000 throws, about 300 would land on a head. That's my prior belief. And here's the other way around, right? Here you say, well, most of the time it will land on head. That's my prior belief. But it's up to you to choose 8 and 4 or 2 or 3. Now, either by looking at the coin, or it could be the result of a previous experiment, right? I mean, if you have already done 100 throws, right? So let's say you start out with A and B equals 1. So you say, okay, I know nothing about this coin. And then basically after 12 throws, and it lands on head 8 times and it lands on tail 4 times, you will end up with this distribution. And then you can go on vacation and you give the coin to somebody else, and you can just pass on all the information that you have about this coin in the form of this distribution as a prior. You say, this is what I know about this coin. I've thrown it 12 times, but you don't have to pass on the outcomes of these throws. You just pass on this distribution, because this distribution summarizes what you know about this coin after these 12 throws. And of course, after like 100 throws, this curve will be a bit different, right? So that's sort of how you should think about these curves. Is that clear?
Yes, so my follow-up question is, okay, why did we choose beta distribution in the first place and not something else?
Yeah, so that's expressed here. You can choose anything else. It's really up to you, right? I mean, you have to choose a data generating distribution, and you have to choose a prior. And really, I do not want to prescribe what you choose. You can choose any model that you like. But if you choose a Bernoulli distribution, all right, that kind of makes sense, right? From as an interpretation of the physics of throwing a coin, that, well, there is a probability for heads in this coin. I don't know what it is, but I'm gonna call it mu. And once I know that, I can write down my data generating distribution, right? The data generate, I can write down what's the probability that I find small n heads and capital N minus small n tails. Well, that's this probability. This is called the Bernoulli distribution. That kind of makes sense. It's really simple, and it sort of reflects the physics of throwing a coin. Then the next question is, now if you get observations and you want to learn about mu, you first have to state you are forced to, well, what do we know about mu before I start throwing these coins, before I make the observations? You don't have to choose a beta distribution, but the nice thing about the beta distribution is that if you're going to have to multiply them, right? Because you have to multiply this likelihood with the prior. And if you multiply the beta with this Bernoulli distribution, then you get another beta distribution, and you can, so it's an analytical answer, and you can use that analytical answer as a new posterior, as a new prior, let's say, to give it to somebody else, right? So you get, the main reason is that you get a very nice analytical answer. And by changing these knobs, these alpha betas, you are very likely be able to express what you believe about this coin. So it's a flexible distribution that allows you to express different kinds of beliefs. And it's also a distribution that gives you an analytical answer if you choose the Bernoulli distribution as your data generating distribution. So they kind of go together. We call this the binomial of the beta. It's a conjugate prior for the binomial or for the Bernoulli, because you get the prior, the functional form, the beta turns into a beta posterior. So they kind of are sort of pairs that match together. That's the reason. But if you say no, I don't want a beta distribution, I want some kind of a Gaussian distribution, then, well, my first answer would be, is that the right one? Because the Gaussian distribution is a distribution over, would allow probably for mu to take on all real values, right? Also lower than 0 and higher than 1. But you can, maybe you can make some, let's say, I squeeze that Gaussian through some sigmoid function, and that becomes my distribution. Okay, well, if that's fine, but then you don't get this nice property, this nice computational property.
Right.
Yeah.
Thanks. Yeah, I just have one more question. In the theory part, it's regarding why MLE is a good approximation to Bayesian machine learning,
Yeah.
and also we an MLE and map converges to an MLE only when its prior is uniform. So when I say a prior is uniform, it means that the parameters can take any values between the interval with equal probability, right?
Yeah, it means a uniform prior, which is, let's say, what we just showed here, right? This is a uniform prior, right? It just means that all the outcomes are equally likely, right? But it is a state of belief, right? It means that you think. I mean, if you know nothing about a coin, nothing, you may just start this way, just by saying, okay, I want to express that any outcome, or that mu could be any value with equal likelihood, right? No, okay, then choose the uniform distribution. If you do that and you multiply, let's say, your likelihood with this prior, it doesn't change the likelihood, right? And it makes no difference. So that's what I mean by when I say here, maximum likelihood is map with uniform prior, because the map is basically execute Bayes rule, right? The outcome of this multiplication is basically, well, is the posterior, but you still need to normalize it by the evidence. But you know that the evidence is not a function of theta, so it doesn't matter. And so we call it maximum a posteriori. So the maximum here of the posterior distribution, or the location of the maximum. But there is a prior involved here. However, if this prior is uniform, so if it has basically the same value for every value of theta, yeah, then it makes no difference. Then you can just take it out, and yeah, then what's left over is maximum likelihood. Now, if we also talked about that if you have a lot of data, then the prior becomes less and less important. So it's true that if you have really large data set, that the difference between maximum a posteriori estimate and a maximum likelihood estimate sort of disappears, right? They become sort of the same. And also the Bayesian posterior becomes more and more a peaked function. So also the Bayesian posterior, in a sense, goes over to a point estimate. But then you need lots and lots and lots of data. The good thing about Bayesian machine learning is it works always. It works also if you do not have a lot of data. You can also do Bayesian machine learning with one data point or two or three. You can also, as you notice that when we score our models with evidence, right? Let's go back to that evidence equation here. So we score the model with evidence. I'm using the entire data set here, D, every observation. I didn't split my data set in a training set and a test set or a validation set. No, I use the entire data set. I want to use everything, right? Because if you need to split your data set in a test set and a training set, and then score your model on your test set, well, then the result depends on how you split your data set, right? If I would have chosen a different split of the data, I will get a different result. So that is, well, it's not an optimal way of scoring a model, right? In Bayesian machine learning, you don't have any of these issues. You use all your data for training, and because of this complexity term, you will not overfit. You will not just fit the data, but there is also a pull backwards to what your, let's say, your old beliefs were, and therefore you will also still generalize well. And you don't need to split your data in a test set or training set. It just works out, let's say, in a perfect way. The only thing is, can you execute this integral? Can you execute this? Can you compute this, right? So the only issue with Bayesian machine learning is the computational aspect. I mean, it is the way to do machine learning. It just may be computationally sometimes extremely hard and even infeasible. So let's say deep learning is a field where people have considered it usually very difficult to apply the Bayesian method to deep learning. I think this is changing now a bit, and in 10 years, all deep learning will be Bayesian. For various reasons, it makes everything a lot simpler. You don't need to choose a training set or a validation set or a test set. You don't need to come up afterwards with how I'm going to score my model. You just use Bayesian evidence to score your model, right? And you know that it's the correct way. Yeah, let's say the computational methods to do so are still a bit under development. And that's why at this point, yeah, if you use deep neural nets quite often, it's a good idea to split your data in a test set and a training set. Just do gradient descent on your weights, so you don't get a posterior, right? You just get some values and then you score it on the test set. There's nothing wrong with that, but it's not, let's say, theoretically the proper way to do machine learning. I think the Bayesian approach is the right way. Which is not to say that in practice you can't choose other methods with lots of success, of course. Okay, I hope I usually talk a lot more than I should, right, for when I do an answer. I hope that doesn't bother you.
No, not at all. I think you cleared my other doubts as well.
Okay. Yeah, any other questions? I still see a hand by you also like that, but
Yeah, I'm not sure if others have a question, and but if I could still ask some more questions, then I can
sure.
ask now. Okay.
Yeah.
So there was a question in the assignment where we want to find the map estimate. So so far, if we calculate the Bayesian posterior, we do the we you mentioned that we'll be doing the scaling later on when we want to compare the models, right? And I was not able to understand why we had to divide by the variance to get the map estimate.
Okay. Yeah. I mean, I have to say I don't know exactly what question, what exercise you're talking about. So maybe this is something you can point out in Piazza, and there I will answer then. But generally, if I get it, I'm not sure if this is what you mean, but maybe your question is, why is it enough to just multiply likelihood with prior and sometimes don't care about dividing by the evidence? The reason, I mean, it's the P of D given M is just a number, right? It's not a distribution. I fill in my data here, and so this is an I just it evaluates to a number 5 or 6 or 7. So it just scales this posterior. It just scales it such that it will always that after you have scaled it, after you have divided by evidence, then you are guaranteed that if you integrate over theta, it will sum to 1. But if you're only interested sometimes in let's say the maximum of the posterior, then you don't really care how if it integrates to 1, right? You don't really care. Also, sometimes it's rather than computing the evidence, it's a lot easier to just multiply these two. Let's say, particularly when you in a discrete over this, if theta has just a discrete alphabet, then you just multiply these two, and then you just sum afterwards over the sum over all values of theta, and you divide so that so that you are sure that it integrates to 1 or sums to 1. So this is the correct formula, but since P of D is not really a function of theta, that sometimes you don't care about it. Sometimes.
Okay, so I'm a little confused. So we can't calculate P of D, right? Because that's literally what we're trying to find some models with some parameters uh, that can say that, oh, this is how this data set looks like. This is how the distribution of the data set looks like, right? So do we calculate P of D after the model fitting?
Yeah, I mean, the objective of machine learning is you choose P of theta, you choose P of D given theta, right? You choose this. And then your objective is to come up with let's say, the alternative decomposition, namely P of theta given D times P of D. That would, if I do P of theta, so if I do write P of D here to the left-hand side, then it says P of D, P of theta given D times P of D, which is just a joint over theta and D. And on the right-hand side, I also have just a joint over the data and theta. So they're both the same distribution. I provided it as a prior and likelihood, but what I'm interested in is to get the other, let's say, decomposition in terms of posterior and evidence, because the posterior reflects, okay, what is now what I know about my parameters after I've incorporated the data, so machine learning, and the other term, P of D, which is really P of D given M, it scores my model. How good is this model in comparison to if I had chosen another model, right? I could have chosen not the Bernoulli with the beta, but let's say your choice, some other model, and we could have compared then the evidences for our models. And if you scored better, then I have nothing on you. I have nothing to say. I can only say, well, you chose a better model, so your model wins. But that's so they are and the way to go about it technically is once you have prior and likelihood, you can compute the evidence by integrating out or summing out the parameter theta, and that's how you compute P of D. And once you have P of D, well, then you can do this division and you get a posterior. Sometimes this integral to get the evidence is just very hard to do, right? P of theta times likelihood, and then you write an integral. It may just not be an integral that you can really compute. You can then still compute the posterior sometimes by just multiplying these two and say, oh well, I got my I got here posterior, but it's unnormalized. I have to sort of divide it by some number so that it integrates to 1. And then you look for that number, right? Then you just integrate this resulting thing. So there may be different sequence of computing posterior and likelihood from prior posterior and evidence from the prior and likelihood. But in principle, the Bayesian inference is about establishing or computing both. Sometimes you don't need the evidence, and you're only interested in the posterior or only the maximum of the posterior. If you only care about the maximum, let's say the map value, then you don't need the evidence.
Yes, thank you so much.
Okay, good. Anybody else? No? Okay, I think that's a good point to finish up because we are more than 45 minutes into it and we don't want to make it too long. If there are any more remaining questions, just post them in Piazza, right? At any time during the whole course, you can always go back to earlier lectures and pose a new question about the lecture, right? So it's not like we move on now and I will not ask or answer questions about this lecture. Just, go back, study it again, write a question in Piazza and we'll answer it. We only do these, let's say, these verbal sessions, for questions that we can't answer in Piazza, or that are just, so we sometimes just easier to talk about things. So with that, I think we're set for Friday. So Friday is going to be a probabilistic programming lecture by Wouter. I hope everybody has been able to set up their Julia setup. If not, just let Wouter know in Piazza, and then we can work on that again. If nothing else, then I will sign off and I will post this one. So it's been recorded. I will post it and on the website again, and we'll see you on Friday. All right.
All right. Hi,
Yep.
Can you hear?
Yeah, I can hear you.
Okay. Yeah. I'm sorry. There's an internet outage where I am, so it's a bit difficult to transmit. So for Friday, indeed, as Bert said, if you haven't yet been able to install Jupyter Julia, that's it, Jupyter and Julia, then please do have a look at Piazza. There are already quite a few pointers to problems that you might face this year.
Someone's asking a question now.
The programming lecture dude is saying something.
What is he saying?
Right. Yeah. So there are already quite a few pointers. So every year there are version upgrades to Jupyter and Julia, and we don't know exactly when they happen. So there was a version update for Julia last week. And so that means if you go to the website of Julia now, you will find a version called 1.6.4, whereas the installation guide for this course was written with the version 1.6.3. Whenever there are version mismatches, either between Jupyter, between Python, between Julia, or one of the software packages that you need for Julia, then sometimes you might run into errors. Please post them. I will figure it out for you. I am currently uploading a package that lets you install Julia 1.6.3 for Windows and for Linux. I don't have a Mac version, but we might be able to find one. And they'll be uploaded to Canvas because that's easier with the large files. And using those packages, using those installers, you can just follow the software guide, and most of the problems, issues should be fine. You should be able to avoid those. In principle, the probabilistic programming sessions will be very similar to Bert's theory lectures. There'll be a video guide. Please just try and follow it along. I'll go through the notebook explaining all of the steps. You can still have a look at the notebook. It's available in lecture note form. But unlike the theory lectures, I do encourage and slightly expect you to also play around with the code in the probabilistic programming notebooks a bit. They're there for you to develop an intuition for some of these concepts. So, for instance, you get to play around with the shape and rate parameters of the beta distribution to see how this thing evolves and shapes itself for certain parameter regimes. And that'll help you understand how you can do inference, how you can do belief updating, and how you can obtain these mysterious distributions, how you do certain computations, what is easy, what is difficult, what is what is intuitive. So good luck, and I'll see you Friday.
Okay, this is Bert again. I just see there were 2 more questions in the chat and that I missed. I apologize. I'm gonna just answer those and then we'll sign off. So the first question is under the heading prediction with multiple models. It's stated that if you need to work with one model, you could select the model with the largest posterior. And the posterior would be the probability for, say, model M given the data. And why would you choose the largest? There isn't really a reason for it other than what is the alternative, right? I mean, the Bayesian computation ends after you have computed posteriors, right? The best you can do if you say you have multiple models is to well, you follow probability theory, you get this equation that sort of weighs the predictions of multiple models. And for whatever reason, you say, well, my computer is too small. I cannot have 20 models making predictions. I can only choose one. Which one should you choose? Well, I would choose the one with the highest posterior probability. That seems, but again, and this is the same thing as for why would you choose map or maximum likelihood? This is decision theory. It depends on what are your personal criteria for making a decision, right? It's not part of Bayesian probability theory per se to make that choice. So if you have good reasons for another choice, that would also be fine. And then the second question is, I was wondering what changes in the computations when we use classification instead of prediction. Well, we're going to do classification later on, so we'll get to there. But really, what happens is you will have in your model a variable that represents the class of your observations, right? Let's say a variable that says, well, it's an apple or a peach. And what you get then your observations, which would be, I don't know, like an image of a piece of fruit. Yeah, so all the pixels. And what do you want to compute? Well, the posterior distribution P of the class, which given, well, the data, the pixels, right? So every question in machine learning usually can be answered by writing down the probability for something that I want to know, given the probability that I already know. In this case, what do you want to know? Well, the class. So, okay, then the probability for the class given, well, what do you know? Well, I see these pictures, right? So given the pixels, that's how you do that. And we'll go to that in the next few classes. All right, so it's a long lecture, but it's okay, I think, for this one, because this is an important one. And yeah, then we'll see each other on Friday. I'm going to stop the recording.